I think we can continue with the second part of today's webinar. It is a pleasure to introduce the next presentation, which is quite important for the practitioner. It is the verification of structural members and detailing of ductility. And the presentation is given by Denis Davi. He's a highly specialized bridge engineer working at CEREMA, which stands for the Center of Studies and Expertise on Risk, Environment, Mobility and Urban Planning. He completed his studies at the French State Public Works Engineering School and the University of California in San Diego. He has more than 20 years of experience with large-scale projects and design and repair of structures. He's a member of the French Association of Earthquake Engineering and convener of the National Mirror Group, as well as the Working Group 6 on European level. So it is a pleasure to leave the floor to Denis Davi. So please start your presentation.
Thank you, Christophe. Good afternoon to all. I will present chapter 6 and 7, which are dedicated to the verification of structural members and detailing for ductility. So here's the content of chapter 6, where I highlighted in red the main points of interest, new features and key changes compared to the previous version. And those are the points I will mainly focus on. And they deal with general statement, material requirements, design for DC2 and DC3, verification of significant damage limit state, capacity design effects, concrete members, foundations, concrete abutments, verification for displacement-based approach, and verification to other limit states, i.e. near collapse, damage limitation, and operational limit states. So some general clauses. First of all, clause 6 should be applied to the earthquake resisting system of bridge design for DC1, DC2, and DC3, which means bridges where you have a rigid connection between the piers and the deck, because bridges equipped with anti-seismic devices, one should refer to clause 8. For cable-stayed and extradosed bridges, one should refer to clause 9. And for integral abutment bridges, we should refer to clause 10. So clause 6 is really dedicated to DC1, DC2, and DC3 bridges. It should be applied for the design of structural members and for the detailing of critical regions of each member type. Detailing is mainly in chapter 7. And outside the critical regions, the detailing of structural members should only satisfy relevant provision from part 2, Eurocode 2, sorry, for concrete structures, Eurocode 3 for steel structures, and Eurocode 4 for composite steel bridge structures. Some material general requirements. The class of concrete should be higher to 25 megapascal in primary seismic members. The reinforcing steel should be made of rebar bars in all regions of primary and secondary seismic members. The reinforcing steel should be of class B everywhere in primary seismic members, except if the structure is designed for DC3. In critical region, then you should use class C reinforcing steel. In steel and steel concrete composite bridges, the material properties in the dissipative zone shall ensure the plastic deformation, that the plastic deformation occur where they are intended to. For this matter, the steel grade and dissipative zones should be specified and noted on the drawings, and higher grade should not be supplied for these zones to ensure that the capacity design is well calibrated on the real grade property of the steel structures. For the verification of significant damage limit states, for force-based approach, the verification should be carried on in terms of local resistances, and the demand on non-ductile members should be should be derived from capacity design effects, which I will explain now. And those capacity design effects are here to ensure that the brittle and other undesired failure mechanisms are avoided. And it is illustrated by the figure below. Here, figure A is for a cantilever pier. Figure B is for a cantilever pier with significant higher mode effect, which you can see on the top here. And figure C is for a pier that frames into the deck and it's designed to form plastic hinges at both ends on the top and at the bottom. The capacity design moment is expressed from the design flexural resistance of the adjacent plastic hinge, and which is multiplied by 3 factors. The first factor, which is an NDP, is the overstrength partial factor. It is 1 in most cases for flexural design, and it is 1.1 for the verification of shear mechanism. Actually, this factor replaces the previous brittle failure factors. Then you have a factor which accounts from the material randomness, which the value of which is 1.15. And then a factor here for the strain hardening, which is 1.05 for reinforcement steel in reinforced concrete members. In the case the normal light axial force is higher than 10%, the gamma RD should be multiplied by this coefficient here. And it should be noted that the coefficient here that accounts for the randomness factor should be omitted within the length of the member that develop the plastic hinge. This because there is the assumption that the longitudinal reinforcement along the pier portion encompassing the critical zone and the zone adjacent to it are from the same steel production. So you don't have to multiply by the randomness factor because it's basically the same steel fabrication. MED should not be greater than MRD, which is with a constant value on the entire length of the critical region LCR, which is shown here with the straight line here, 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 and there. So for concrete members everywhere, the capacity should be higher than the demand. In structure of DC1, the demand MED is directly derived from the analysis. And for shear resistance verification, the seismic action effect should be multiplied by the behavior factor Q, as is the case in the current version. Whereas from DC2 and DC3, the demand is accounting for the capacity design effect with from the M0 here. And the shear resistance is also from the capacity design effect, but with here a gamma RD coefficient being 1.1 instead of 1.0. For the joints adjacent to critical region, I will not enter into the detail of this slide. Basically, the same principle as previously, always based on capacity design related to the yield capacity of the reinforcing steel in the joint. For the deck verification, it is stated that there is no significant yielding should occur in the deck. Significant refers to yielding of the reinforcement of the top slab of the deck yields up to a distance from its edge equal to 10% of the top slab width, or up to the junction of the top slab with the web, whichever is the closer to the edge of the top slab. So this is basically the same as before. For bridges in DC1, so no significant yielding should occur in the deck under the most advanced design action effects from analysis, with significant reduction of the torsional stiffness of the deck from 5.1.1 as Paolo explained before. and for bridge of DC2 and DC3 under the capacity design effect with assumed torsional stiffness equal to 70% of the previous value here. For steel and steel concrete composite members, the energy dissipation shall be considered only in the piers and not in the deck. And the member of dissipative zone should be of cross-sectional class 1 in DC3, 1 or 2 in DC2, and it may be of cross-sectional class 3 when Q equal 1.5, i.e. in DC1. For other clauses, they refer mainly to capacity design principle from 632 and from the part 1 to the clause 11 for steel and composite and steel concrete composite members. For what concerns the foundations, the bridge foundation system should conform to part 5, clause 9, with the note here that the elastic response of structural members of the foundation is preferred for bridges, as indicated in 431, as Paolo explained before. Non-yielding piles are preferred, designed according to part 5, clause 954, unless it is shown that they can be inspected and repaired according to 433, with typical configuration where this is possible are those where piles are arranged in only one row. And then I noticed here some relevant clauses from part 5 that are applicable to bridge foundations. Here we have a warning that on different foundation type for different vertical elements, basically it is not recommended to use shallow foundation on one pier and pile foundation on another one. Here we have clause 9.2 for the determination of design action effect, clause 9.4 for resistance verification of surface and shallow embedded foundations, and clause 9.5 for the resistance verification of pile foundations. And all this was presenting in the webinar of part 5. For connections, there is a minimum overlap length here to avoid unseating, and I think Telemachos will present this after me. Here we have avoidance that all bearing uplift at the same support unless it has no detrimental effect on the bearings. And for concrete abutments, it is stated that all main structural components of the abutment should be designed to remain elastic under the design seismic action, unless the back walls, which are structural components that can be designed as sacrificial elements. So we have two types of abutments. For abutments flexibly connected to the deck, one should refer to part 5, since it can be assumed to be an isolated earth retaining structure. And for abutment rigidly connected to the deck, one should refer to clause 10 of part 2, which deals with integral abutment bridges. For the verification of displacement-based approach, for what concerns the bending within critical regions, so for significant damage limit state, it is based on this general equation, with the demand in terms of displacement, which should not overpass this value, which is the value at yield plus a percentage, which is 50% of the gap between yield and collapse. In response history analysis, for the verification of local deformation within critical regions, one can use the biaxial interaction model from Eurocode 2, which is this equation here, taking alpha n equal to 1.5 and replacing here the acting and resisting moments by the chord rotation demand and capacities. So it's basically the same equation from Eurocode 2, but adapted to the displacement verification, seismic displacement verifications. Outside the critical region, bending and shear verification should be carried out in terms of forces. So the displacement displacement-based approach only concerns the rotation of the plastic hinges. For the verification to other limit states, for near collapse limit states, verification should be carried out in terms of displacement-based approach. Here, using the very end of this curve here, via non-linear static or response history analysis, since the seismic action at this limit state can drive the structure into the non-linear range to an extent where the results of linear analysis are less reliable than they are at the significant damage limit state. So it's strongly recommended to use displacement-based approach via non-linear static or response history analysis. The core rotation capacity has to be evaluated depending on the material and according to part 1.1 plus 7. And for the verification of damage limitation and operational limit states, which are basically the same principles because the structure remains elastic, the verifications may be carried out in terms of force or displacement-based approach. If the force-based approach is used, the displacement should be calculated using the spectral displacement multiplied by the displacement amplification factor, which is called here the Q disp, because dr has already been divided by Q in the spectral response. And mainly, it is said that the relevant criteria should be agreed with the relevant authority, since it deals with the functionality of the structure. Now let's go to the chapter 7, which deals with the detailing for ductility, with here general statement, concrete piers, with general requirements, requirement for critical regions, buckling of longitudinal compression reinforcement, and some requirements for foundations. In general, it is said that the clause 7 should be applied to primary seismic members, i.e. piers and abutments of bridge designed to DC2 and DC3, which means that for DC1, there is no specific detailing related to the seismic design. Only the detailing from Eurocode 2, for instance, should be applied. In concrete piers, the longitudinal reinforcement ratio should be higher than 0.5%. In the previous version, it was 1%. The diameter of the bar should be higher than 16 millimeters. For hollow piers, we still have the requirement that the width should be higher than the interior dimension divided by 8 for circular or rectangular. For the critical regions, the length of critical regions is the maximum of the depth of the pier section within the plane of bending, i.e. perpendicular to the axis of rotation, and the distance between Mmax and 0.8 Mmax, which is figured here and there for single bending or double bending. And should not be higher of 1.5 the value from A. This is when the actual ratio is less than 30%, and when it is higher of 30%, the value of the critical region length is increased by 50%. It should be noticed that the length of critical region is only for detailing of the reinforcement and not for estimating the plastic in rotation. For the plastic in rotation, you have another equation. The longitudinal reinforcement should be constant and fully effective over the length of the critical region, which means that there is no splicing by lapping or welding of the longitudinal reinforcement within the critical region. So this is not allowed. For confinement in the critical region of primary seismic members, it should be achieved through rectangular or circular hoops or cross ties or spirals with a diameter higher than 10 millimeters. There is a note stating that if spirals are used, it is recommended to arrange them in 2 or more independent strands so that if one is broken, the stress can be reported on the others without everything to be be broken and not efficient. The quantity of the confining reinforcement is defined through the mechanical reinforcement ratio here, with the transverse reinforcement volumetric ratio expressed by those equations for rectangular and circular sections, and the associated quantities are different from rectangular and circular, and from DC2 to DC3. Of course, for DC3, it is the reinforcement ratio is higher than for DC2. This ratio should be provided over the entire length of the critical regions. It should be gradually reduced outside the critical region, but not less than 50% over an additional adjacent length of LCR. Still for confinement, here we have the required value of the longitudinal spacing SL, which should be less than 6 times the diameter of the longitudinal bar, or 1/5 of the smallest dimension of the concrete core. And here the value for the transversal spacing, which should be less of the minimum of 1/3 of the smallest dimension of confined concrete core, or 200 millimeters for this value being less than 1 meter, or 300 millimeters for B-min higher than 1.5 meters, and it's linear variation between those two values. Here some figures illustrating possible rearrangements of the hoops. And here some clauses referring to the buckling of the prevention of buckling of longitudinal compressional reinforcements, with longitudinal spacing being less than 5 times the diameter of the longitudinal bars, and the transversal spacing being less than 200 millimeters. And then you have the minimum amount of the confinement or the anti-buckling rebars. Here we can altern 90-degree hooks with 135 hooks, with an alternance 1 over each 2 spirals, not spirals, cross ties. Here some figures representing the arrangement in joints adjacent to critical regions, which are basically the same as before. And for foundations, we just refer to clause 5, to part 5, clause 9.4 for spread foundations, and clause 9.5 for pipe foundations. And I think it's my last slide. So yes, if you have any questions, I will try to answer them. Thank you.
So thank you very much for the well-structured presentation. And we have time for 1 or 2 questions. And maybe one question from my side. So I think you introduced the verification in case of application of displacement based design.
Mm-hmm.
So there was a reference to part 1.1. Could you give a comment on the thresholds that are given in part 1.1 for the rotation capacities? So is there a difference to the Eurostructures, especially for bridge connections for the joints, or?
The capacity rotation, yes, I think it's pretty well defined in part 1.1 and more detailed than it was before. So there are many specifications, mainly dealing with the confinement efficiency, and this is pretty well detailed in part 1.1. So I will not enter into the details, but it's very well defined there, depending on the effect on the confinement, on the capacity curve of the confined concrete, on the efficiency of the confinement steel, depending on different arrangements and so on. I think the equations are a little bit more complicated, but more precise to apply and more reflecting the theory, I guess.
Okay, and the requirements are, let's say, comparable to usual structures, or there are higher, or there is not.
It's not higher. It's always based on the general capacity curve and the coefficient of the one which is equal to 50% for significant damage. This is just for near collapse limit state and so on. But this is radically new and very well explained in part 1.1. But it's always based on this capacity curve and the amount of plastic zone which is attained in one or the other of the different limit states.
Okay, thanks. So I don't see any.
Maybe Paolo can complete on this part. I don't know.
Yes, of
Yes, Christophe. Yes, Denis. All the deformation models, deformation capacity models, are split between part 1.1 and part 3. Part 1.1 provides the basic models, not just for reinforced concrete, but also for other materials like steel and composite steel structures in clause 7. And these models are for code compliant detailing. So this is just what you need for the purpose of design. And then, just to give you further information, in part 3, you have how the provisions to modify those models to account for older, maybe not seismic details or low code, as would be said in the US, now pre-code or low code, like details for short laps, but still deformed bars, or details for smooth bars with or without hooks. And also, for instance, which is relevant for bridges, you have the shear strength models for members and for joints, because, for instance, joints, if they are code conforming, need not be verified in either force-based or displacement-based design of buildings. This has been greatly simplified in part 1.1. But when you go to bridges, you don't have, let's say, easy beam column joints for which you can give simplified rules. You need also for new bridges to verify the joints, and then you have to refer to part 3 where you have these provisions. And the partial factors, the models cover also for the typical cross-section of reinforced concrete piers or steel piers. So you don't need specifying models in part 2.
Thank you once again for the presentation, and we will proceed with the next speaker.